Okay, so now we're going to continue with limits and continuity of trigonometric, exponential, and logarithmic functions. So in this section, what we're going to do is we're going to find limits involving trigonometric functions. We're going to determine where the trigonometric functions are continuous, and we're also going to determine where an exponential or a logarithmic function is continuous also. So for this section, we need to know these basic trig limits. Basically, that the limit as x approaches 0 of sine of x is equal to 0, and the limit as x approaches 0 of cosine of x is equal to 1. So basically, sine of 0 is 0 and cosine of 0 is 1. Also, we have this theorem that will help us simplify things, and it reads like this. If theta is measured in radians, then the limit as theta approaches 0 of sine of theta over theta is equal to 1. So we need to memorize this theorem, right? So for our first example, we just want to find the limit, and as usual, when we're looking for the limit of any function, what you want to do first is always plug it in, and let's see what we get. So if I plug it in, actually let's read it first. So here we're looking for the limit as x approaches 0 of x squared minus cosine of x. So first, let's start off by just plugging it in. So if I plug it in, we're going to get 0 squared minus cosine of 0. 0 squared is 0. Cosine of 0 is 1, but there's a negative in front, so we end up with negative 1. We have a limit, we have a number, so that is the limit. That is it for that. Let's go on to number 2. Same thing. Let's plug it in, see what we get. So if I plug it in, it'll be sine of 0, and then divided by 1 plus cosine of 0. Now we already know what sine of 0 is. We know it's 0. And then we have 1 plus cosine of 0 is 1. So there we go. So here we really have 0 over 2. And 0 over 2 is just 0. So we have an answer, and we're done with that. Okay, example number 3. Let's do it again. Plug it in. So if I plug it in, we have natural log of, so x is approaching 1. So that means that the x becomes a 1. This one becomes just e. So we have 1 over e. So what we can do here is rewrite it as natural log of e to the negative 1. And that exponent, we can write it in the front because that's one of the properties of logarithm. So it'll be negative 1 natural log of e. And remember that whatever number is in front of the logarithm, you're going to multiply by the result. So natural log of e is something that we need to know, and it's negative 1 times natural log of e is 1. So that means that our answer is going to be negative 1 times 1. Okay, let's find another limit. So here we go. Let's do this again. So if I plug in, right, so this time we want to find the limit as theta approaches 0 of sine of 3 theta over theta. So if I plug it in, this time I'm going to do it over here because I know something's going to happen. So 3 times 0 over 0, that gives me sine of 0 over 0, but sine of 0 is 0, so we end up with 0 over 0. So that's not possible. We have a limit that it's indeterminate. It's an indeterminate form. So what we need to do is kind of manipulate it like we've been doing. So notice that this time we have 3 theta in here, and it's being divided just by theta. So what I want to do is multiply by 1. So this is how we're going to do it though. I'm going to say limit as theta approaches 0. Now since I want to multiply by 1, that 1 is really going to be 3. Let me fix this. It's going to be 3 over 3. That's 1 sine of 3 theta times theta. Now, we're going to use limits of properties. What I'm going to do is I'm going to get this 3 and move it to the front. That's one of the properties. So I'm going to get this 3 and move it to the front. I'm going to leave this 3 alone. So it'll be 3 limit of theta approaches 0 of sine 3 theta over 3 theta. Now, notice that this inside angle measure of sine matches this denominator. They have to be the same in order for me to apply that property. So now that I have limit as theta approaches 0 of sine of 3 theta divided by 3 theta, notice again, this is the angle, and this number down here, they're exactly the same. Now if I plug in a 0, it'll give me 0 over 0. But that's okay, because according to the theorem, that becomes 1. So this right here becomes 1. So in reality, what we have is 3 times 1. And 3 times 1 is just 3. So that is our limit. Okay, let's try another one that's a little more complicated. So again, we could do this in our head. If I plug in, if I want to find this limit as theta approaches 0, and it's sine divided by sine. Now if I plug in the 0 here for theta, that's going to give me 0. That's going to give me 0. And sine of 0 over sine of 0 is just 0 over 0. So we need to, again, manipulate it. This time's a little different. So this is what we're going to do. So we're going to write limit as theta approaches 0. Now, let's see. What we want to do is make sure that this sine has a 5 theta in the denominator, and then this sine has a 2 theta in the denominator. So we have to do 2 fractions. So the first one is going to look like this. We want to have sine of 5 theta, and then we're going to divide by 5 and multiply by 5. That's really multiplying by 1, so nothing changes. Everything stays the same. Let me change the color so you can see what I'm doing. So it'll be 5 over 5. We're going to do the same thing with the other sine. So sine 2 theta, and then it's going to be 2 over 2. That's 1. So we're really not doing anything different. I mean, we're multiplying by 1 literally. So now we just need the theta now. Now if I do, if I write theta here and theta here, remember that if you have a complex fraction and you have like 1/3 over, I don't know, 2/3, then we're able to cancel the 3's because they're both in the denominator and they're exactly the same. So in reality, nothing changes. Well, here it's the same thing. I would just cancel them out. So in reality, we're really just multiplying by 1 again. Okay, so we'll leave it like that. So now what I'll do is we're gonna get this 5, and we're gonna move it to the front, and then we're gonna get this 2, and we're gonna move it to the front. But the 5 is gonna end up in the numerator, and the 2 is gonna end up in the denominator. So here we have 5 over 2 limit as theta approaches 0. And then we're going to have a complex fraction now, where we have sine of 5 theta over 5 theta divided by sine of 2 theta over 2 theta. Now, if I take the limit as theta approaches 0 of this function here, that's going to give me 0 over 0. But according to the theorem, it really becomes 1. And when I do the same thing for this one, the limit is also going to be 1. So now we have this. We have 5 over 2 times 1 over 1, which in reality is just 5 over 2. And that is our answer. Okay, so now we want to find the limit as x approaches 0 of this function. Now we can do this in our head, just plug it in. So if I plug in a 0 here, it gives me 0. And then sine of 0 is going to be 0. So now we know it's going to be 0 in the numerator. Denominator, this x becomes 0. And 0 times whatever this is still 0. So again, we have 0 over 0. So that tells me that I have to somehow manipulate it. So this time, what I'll do is I'm going to split it up. So what I'll do is I'll write it like this. Sine of 3x over x times 1 over cosine of 4x. That's the exact same thing. I can do that. So now what I want to do is I know that if I take the limit as x approaches 0 and somehow I can make this equal 0 over, it's already 0 over 0, but if I can make this look like the angle measure of sine, then I can apply the theorem that we learned at the beginning. So the thing to do is to go ahead and multiply like we've been doing. So limit as x approaches 0. We're going to multiply by 3 over 3. So 3 over 3, it's going to be sine of 3x over x times 1 over cosine of 4x. So that's going to help us now. So what I'll do is, again, I'll get this 3 and I'll move it to the front. So it'll be 3 limit as x approaches 0. It'll be sine of 3x over 3x times 1 over cosine of 4x. Now this is exactly what we wanted, so we can use a theorem. So notice 3x, the limit is approaching 0. So now I can apply the formula that tells me that that limit's going to be 1. So it'll be 3 times 1. Now, when I take the limit of this one, and x is approaching 0, so that means that we're going to end up with cosine of 0. And cosine of 0 is just 1. So in reality, that's also 1. So my final answer is just going to be 3 times 1 times 1, which is equal to 3. Okay, so once again, let's do a different example. Now we're going to plug it in. Now, for this one, when you try plugging it in, we're going to get, let's see, it's a limit as x approaches 0. So we're going to use direct substitution. We know the denominator is going to be 0, so that's going to be a problem. Sine of 0 is going to be 0. Now I have 0 over 0. That's going to be a problem. Cotangent of 0, doesn't exist. And cosecant of 0, that's also going to be a problem. So what we're going to do is we're going to have to rewrite everything in terms of sines and cosines. That would be the best thing to do. So let's rewrite it first. So it'll be limit as x approaches 0 Now, let's see. Cotangent is the same as cosine over sine. So we're going to write it as cosine of x over sine of x minus, and then cosecant is 1 over sine, so it's going to be 1 over sine of x times sine of x over x. Okay, this still hasn't helped us any, so we need to simplify. We just rewrote it. It's still the same thing. So now what I'll do is these two fractions, I'm going to write it as 1 since we have the same denominator. So it'll be limit as x approaches 0 and inside it'll be cosine of x minus 1 over sine of x times sine of x over x. Now we're still going to simplify even more. Now since this fraction here is multiplying with this trig function outside, I notice that I'm able to cancel the signs. Okay, so if we cancel the signs, then we have limit as x approaches 0 of cosine of x minus 1 over x. And this is good because we have a property that says that if you have the limit as x approaches 0 of cosine of x minus 1 over x, the answer is going to be 0. So we need to memorize this. So look, if you plug it in, if you would plug it in, cosine of 0 is 1. 1 minus 1 is 0 over 0, so it's indeterminate. So there's this property that I want you guys to learn. And it says that if you have the limit as x approaches 0 of cosine of x minus 1 over x, that's equal to 0. So that's one property we should memorize. Okay, on to number 8. Here we have we want to find the limit as theta approaches 0 of cosine of 4 theta minus 1 over 2 theta. Now, if you use direct substitution, again, when you replace theta with 0, this gives me cosine of 0, which is 1. 1 minus 1 is 0, so I'm going to get 0 in the numerator. Denominator is going to be 0 also, so that's going to be a problem. So in order for me to use this property, this one, we want to make sure that the angle measure inside matches the one that's in the denominator. So we're going to manipulate it like we've been doing the other ones. So what I'll do is going to rewrite it. So limit as theta approaches 0. Now if I want to make this 2 theta turn into a 4 theta, then I have to multiply it by 2. But I have to also multiply the numerator by 2, not just the denominator. So now we have, let's see, cosine 4 theta minus 1. So I'll do what we've been doing, where I get this constant and then move it to the front. So it'll be 2 limit as theta approaches 0 cosine of 4 theta minus 1 over 4 theta. Now we can use that property, this one right here. So this leads to 2 times 0. This right here, this becomes 0. So our final answer is just 2 times 0, which is going to give us 0. Okay, for this one, what we want to do is find the limit of, the limit as theta approaches 0 of tangent theta over theta. So first thing, like always, let's use direct substitution. So if I plug it in, we get tangent of 0 over, I put theta. Tangent of 0 over 0. But tangent of 0 is 0, so we have 0 over 0. So again, that tells me that I have to somehow manipulate it. So what I'll do is rewrite tangent in terms of sines and cosines. So let's do that. So limit as theta approaches 0. So tangent is sine over cosine. So I'll write it as sine theta over cosine theta over theta. I want to simplify this. So imagine theta being over 1. So we can use that little trick that I taught you where you multiply these two, and they go to the numerator, and then these two in the denominator. So it'll be limit as theta approaches 0, sine theta over theta cosine theta. Now, just to make things simpler, we can split it up a little bit. So limit as theta approaches 0. I'm going to rewrite it like this. Sine of theta over theta times 1 over cosine of theta. That makes things easier. So you can just split it up. And then notice that when I take the limit of this one right here, again, the limit of this one right here, as theta approaches 0, that's going to be 0 over 0, but according to the theorem, the limit is approaching 1. Okay, the limit is approaching 1. So I know that this one is going to be, this right here is going to be 1 times. And then when I take the limit of the other one, this one's going to be cosine of 0. Cosine of 0. And we know that cosine of 0 is 1. So in reality, you have 1 times 1, which is just 1. And our answer is going to be 1 times 1, which is 1. Okay, so now we want to talk about continuity. So there's this theorem that says this, that the sine function y cosine of x is continuous on its domain, which is all real numbers. So it's continuous everywhere, okay? It has no breaks, no holes, no jumps, nothing. It's just continuous. Same thing goes for cosine. Cosine of x is continuous on its domain, which is real numbers. And the other trig function, tangent, it's continuous everywhere except where cosine of x is 0. Now remember, tangent is, remember that tangent of x is sine x over cosine x. And it'll be discontinuous or not continuous when the denominator is 0 because it'll be undefined. So we don't want cosine to equal to 0. And that happens when cosine x equals 0, when x equals pi over 2, because cosine of pi over 2 is 0, negative pi over 2, and then 3 pi over 2, and then negative 3 pi over 2, 5 pi over 2, all those intervals of pi over 2. So we say at pi over 2 plus pi n, where n is an element of the integers. So that's where tangent is not continuous. Also, an exponential function is continuous on its domain, which is all real numbers. And a logarithmic function is continuous on its domain, and its domain is greater than 0. It's not equal to 0. So let me erase that. So what that means is this, that whatever you have in here, you have to set it to greater than 0 and then solve for x, and that'll be your domain. Okay? All right, so let's see. Determine whether f is continuous at a number c. Determine whether f is continuous at a number c. So for this one, to find out if it's continuous, we need to use the definition of continuity, which is this. Limit as x approaches c of f of x, is it equal to f of c? Are they equal to each other? If they're equal to each other, then yes, they are continuous at that number. In this situation, the number we want is 0. So is it continuous at 0? So let's set it up. So limit as x approaches 0 of f of x, is it equal to f of 0? So all I did right now is I replaced the c with 0 because that's what it's equal to. So now I have to determine, what do I plug in? So in the last lesson I said that I always like to start with the right side. I want to know what is f of 0. F of 0, what is the value of f when x equals 0? So in this situation, when x equals 0, the function is 3. So this side, it's going to be 3. Now I have to take the limit as x approaches 0. The only problem is that we have, it's a piecewise function, and at 0, we have two options. Less than 0, it'll be this function, 3 cosine x. Greater than 0, it'll be x plus 3. So what I need to do is, we need to take the one-sided limits, because this one is not telling me to take the one-sided limits. It just says at 0. In order for me to find the limit at 0, I actually have to take the one-sided limit. So I have to do that on the side. So I will say limit as x approaches 0 from the left. From the left means less than 0. So that means that we are going to use this function. So it'll be 3 cosine of x. So just plug it in. So we get limit. No, not a limit. We're just plugging it in. So we get 3 cosine of 0. Cosine of 0 is 1. So 3 times 1 is just going to be 3. So now I check the limit from the right-hand limit. So limit as x approaches 0 from the right. That means greater than 0, so I'm going to use x plus 3. So x plus 3, plug it in, 0 plus 3 equals 3. So now the one-sided limits are the same. So what that tells me is that the limit exists and it's equal to 3. So therefore, this limit over here, as x approaches 0 of f of x is equal to 3. So yes, since the limit of f of x is equal to f of c, then yes, it is continuous at c. Okay, same thing. We want to see if it's continuous at at c equals 1. So again, we start off by writing the definition. Limit as x approaches c of f of x, is it equal to f of c? This time c is 1, so let's write it out. Limit as x approaches 1 f of x equals to f of 1. Okay, so I always like to start with the right one. So the value of f of 1, meaning which one is equal to 1. So I notice that this function, natural log of x, if x is greater than or equal to 1, that's the one that I want. So that's going to go on the right side. So I'll just rewrite it as natural log of 1, replace the x with 1. Now that means that I'm going to take the limit as x approaches 1 of the other function, which is just tangent inverse of x. So now we're going to evaluate. And let's see, let me go this way. So all we do is plug it in. So tangent inverse of 1 equals 2. Now natural log of 1 is one of the expressions that you need to know. Natural log of 1 is 0. So now we need to figure out what is tangent inverse of 1. And tangent inverse of 1 really means what angle has a tangent of 1. What angle has a tangent of 1? And that angle is pi over 4. Pi over 4. So pi over 4 equals 0. Well, we all know that pi over 4 is not equal to 0. Pi over 4 is equal to pi over 4. So this is not true. And since this is not true, that means that it is not continuous at c equals 1. And the reason is because the limit is not equal to this. So the limit as x approaches c of f of x is not equal to f of c. So therefore, it is not continuous. So now we want to see if f is continuous, or where is it continuous. So the question is, determine where f is continuous. So here we have cosine of this angle. So cosine, we said at the beginning that cosine is continuous everywhere, but cosine of x is continuous everywhere. That's if it's just x. But this time we have a fraction. So this angle measure inside x was replaced with this other fraction. So since it's a fraction, what we need to do is look at the denominator and see if it'll give us a 0. So if I look at the denominator, my denominator is 2x. And what we do not want in the denominator is a 0. So if I set it equal to 0, 2x equals 0, and I solve for x, I get that x equals 0. So that's what makes this function discontinuous. So what we do is we write continuous everywhere except x equals 0. Okay, 3 more examples. Yes, 3. Isa, 3. Okay, so again, we're going to check for continuity. And this time we have a rational function. Notice that we have a fraction. So what we want to do is check the denominator. When is it equal to 0? So if I set it equal to 0, so if I say 1 plus cosine squared theta, when is it equal to 0? And if I try to solve for theta, so I will move the 1, so I have cosine squared theta equals to -1. And if I try to solve, I'm going to take the square root of both sides. So if I take the square root of both sides, we get cosine theta equals the square root of -1. Well, that's a problem because we know that we cannot have a negative number inside the radical. This is called not real or imaginary. So therefore, that will never equal to 0. So therefore, what that tells me is that the denominator will never equal 0. So the question was, where is this function continuous? And since the denominator will never equal 0, we can just say that it is continuous on all the real numbers. Okay, last two. Again, determine where the function is continuous. So notice right away that it's a logarithm. And for a logarithm, the domain, or the inside here, that has to be always greater than 0. Always greater than 0. So the first thing I look for is the x. So notice that this is x squared. So it doesn't matter what value of x I plug in, I'm going to square it. It's always going to be positive. And then I'm going to add 1 to it. So that makes it positive still. So I know that whatever x value I plug in here, it's always going to be positive. Therefore, this function is continuous everywhere also, because this will never be negative. It's always going to be positive. So we can just say continuous on all real numbers. Okay, last example. Again, we want to determine where this function is continuous. Again, we have a rational function. So what we want to do is set the denominator equal to 0. So we'll have 1 minus sine squared of x equal to 0. Now let's solve for sine. So we'll have 1 equals to sine squared. Take the square root of both sides. We end up with plus or minus 1 equals to sine of x. And the question is, what angle gives you a sine of positive 1 or negative 1? Well, let's see. Sine is 1 when x equals pi over 2. And it's also equal to negative 1 when it's 3 pi over 2. So that tells me that when x is pi over 2, or 3 pi over 2, sine will be 1, and that makes the denominator equal to 0, and that means that it is discontinuous there. So therefore, we can say that this function is discontinuous at every pi over 2, 3 pi over 2, so every multiple of pi over 2. Well, not multiple of pi over 2, but pi over 2 plus a multiple of pi, because from pi over 2 to 3 pi over 2, it's pi. And then 5 pi over 2, that's another pi. Then 7 pi over 2, that's another pi. So we can write it as discontinuous at pi over 2 plus pi n, where n is an element of the integers. So this is where this function is discontinuous.